All right, we're going to get started for the post-lunch session. We have our next speaker is John Osterhout, who's been with us before. He's the author of Homa, which is in some circles an extremely well-known transport protocol. He's also done simple things like TCL, TK, and a few other well-known things that you should read up about. And he's going to tell us more about progress for Homa in the kernel. Thanks, John.
Great, thank you. First, I have to say, this is a fairly surreal lecture hall where we have audience A and audience B. And I feel like I'm on some sort of, I've been ejected into some sort of hyperspace world where I've been cloned, that I'm giving my talk twice to two different audiences, but saying the exact same words at the exact same time to both audiences. And as I was watching this morning, I was thinking, this introduces a really interesting new head scheduling algorithm. Should my head face audience A, or should I face audience B, or should I address my talk to the corner in between you? Or should I time multiplex? And if so, how long should the time slices be? Should I spend a couple of slides to this audience, this couple of slides to this, or should I just go like this word to, and if maybe I swivel my head rapidly enough, I could give the appearance of facing both of you at the same time. But my neck probably can't tolerate that.
You have to assign a skepticism metric and then apply that to the.
Okay, anyhow, I wanted to talk about some work I've been doing on Homa over the last year. So Homa is this new transport protocol that was initially developed by one of my PhD students at Berkeley, and the performance has been so great that I've been trying to see if we could actually make it real and displace some of TCP's traffic in the data center with Homa. And so that's my personal project, been doing whatever it takes to see if we can get Homa adopted. But what's interesting about Homa is that it's based on messages, not the traditional stream-based thing. And Linux and all operating systems and their networking, they're fundamentally based around streams because that's what TCP does, and that's natural. So trying to do a message-based protocol has interesting system implications I've been gradually working through over the last couple of years with Homa. And I want to talk about one of those issues today. And in particular, introducing messages rather than streams. This is actually great for latency. Homa has really superior latency, but it's often challenging for throughput, for reasons I'll talk about in a second. And in particular, the traditional approach to managing buffers, user application buffers, pretty much defeats pipelining in Homa. You can't pipeline like TCP. And so the throughput was not as good in Homa as it was in TCP. And what I want to talk about today is how I fix that by introducing a new buffer allocation scheme. Actually, it was kind of reminiscent about what we heard about with I/O U-ring this morning, where the application provides a big chunk of memory to the kernel, and the kernel actually allocates user space buffers out of that. And by doing that, we've been able to get the pipelining that's as good as TCP's and increase the performance significantly so that Homa throughput is now about the same as TCP's throughput. Okay, so first a little bit of background. What is Homa? Homa is a brand new clean slate redesign of transport for the data center that is different from TCP in every major design aspect. Last year in the keynote, I kind of walked through why every major aspect of TCP's design is wrong and how Homa does it better. But just a very quick summary. The most important thing is it's message-oriented, or more precisely, it's RPC-oriented, where a client sends a request message to a server, the server handles that and responds back with a response message. Homa is connectionless, or what I really should say is it has extremely lightweight connections. It creates a new connection for every RPC and does that extremely efficiently. And so as a result of that, for example, you don't have a socket per connection. You have typically one socket per application, and you can have any number of outstanding RPCs over that single socket. Homa uses SRPT policy, shortest time first. The idea is to prioritize short messages, and I mentioned this morning in a question to Manya the issue about doing run to completion. So Homa is a run to completion protocol. It tries to find one message, get that message finished as quickly as possible, and then go on to the next message. And then it has a bunch of novel things in the way it does congestion control, and in particular, it's able to take advantage of the priority queues in today's switches. I don't know of any other protocol that will actually automatically manage those priorities in ways that provides really great throughput and latency. And if you combine all that together, it's sort of 1 to 2 orders of magnitude faster in terms of tail latency for short messages than either TCP or DC-TCP. So it's a pretty big performance improvement. But as I mentioned in the introductory In fact, in the original version of the system, there was no pipelining at all. You know, the natural way, if you're doing a message, is copy the whole message into the kernel, then transmit the whole message over the network, and then once it's been received, copy the whole message out to user space. And so if you do it that way, which Homa did originally, on a 25 gigabit per second network, you lose almost half of the network bandwidth that way. So TCP gets on the order of 18 to 19 gigabits per second of throughput for 500 kbyte messages on a 25 gig network. Homa was getting 10 to 11, so significant penalty for that. So what I'm going to talk about in this talk is how I fixed that. And oh, by the way, as the networks get faster, this discrepancy gets worse because in a 25 gig network, in fact, the network transmit actually takes longer than either of the copies. And so the lack of pipelining there doesn't hurt quite as much. But when you get to a 100 gig network, almost all the time is actually copies. The copy is the dominant cost. And so this lack of pipelining becomes more and more problematic as networks get faster. All right, so first I'll do the sender side easily. I'm not going to spend much time on that. That was pretty easy to do in that we can start transmitting a message as soon as we've got enough to fill a couple of packets. That's easy to do. The only challenge is the synchronization challenge in that while we're copying from user space to kernel space, we can't hold the RPC lock because that would prevent us from transmitting more packets from that message. And so we have to release the RPC lock, and then the risk there is that it's possible something could go wrong and the whole RPC could get deleted while you're not holding the lock, and then of course very bad things happen because the RPC structure disappears from underneath you. And so we needed some way to keep that alive. You know, the first approach was to think about using RCU, but at least the way I use it, that was not practical for me because the time constants are really long for RCU. Once you've done something RCU, it takes a really long time, like many milliseconds, before you can actually clean the thing up. And Homa, with very, very high throughput of RPCs, we don't want to have to wait milliseconds in order to clean up old RPCs. So that didn't work. I ended up implementing a very simple RCU-like thing with a much faster response time for Homa. And yeah, that was fairly straightforward, not difficult. The other side is really where the challenge is and where I want to spend most of the time. And on the receive side, the problem is the API makes it impossible to pipeline because of the API. Here's an example. So the way you do a receive, of course, is that you call receive or receive message or read or whatever, and you pass in a buffer for the message. Okay, so now imagine some packets arrive from a large message. Well, if we want to pipeline that, we want to start copying those packets into the buffer before we've received all of the packets. So we do that. We've copied some of the packets in. And now the problem is some other shorter message arrives. And it's complete. Well, the rule of Homa is shortest message gets priority. So if a short message is finished, we have to deliver that to the application immediately. We can't delay that behind that long message. But the problem is we've already committed the buffer space to the long message. So we're in trouble here. And the only solution I could think of initially was don't start copying until you've got the whole message so you know you're actually going to deliver this message to the application. That's the only way to do it with this API. So that was the fundamental problem. With the existing API, we simply could not pipeline on the receive side. And so what I did is I introduced a new API for buffer management for receiving messages. And the key idea is that the transport protocol has to have enough buffer space to receive parts of several messages simultaneously. It can have gotten some parts of some messages, parts of others, and then eventually once one is complete, then it passes it off to the application. So that means that the application does not indicate a specific buffer when it calls receive message. Instead, the buffer is returned as a result by the transport. It's not passed in as a parameter. And then Homa gets to choose which of the buffers to return. So that's the basic idea. Now let me just walk through how to implement that. So the idea is that an application creates a socket. And as I mentioned, typically there's only one socket per application in Homa because you can send and receive arbitrary numbers of RPCs to any number of machines with a single socket. So you create a socket, and then after the socket has been created, then you pass in an M-mapped region to Homa for it to use for buffer space for that socket. So the application allocates a large region, hands it off to Homa, and says, this is yours to allocate buffers out of. Then as messages arrive, Homa will allocate space out of that. I'll talk a little bit more about exactly how that works in a second. But the basic idea is Homa will allocate space for those messages. And in this case, we have, the red message has been partially received, and the blue and the purple messages have been completely received. And then when the application calls receive message, then Homa returns to it information about where the buffer is for the message it's returning. In this case, it'll be the purple message because that's the shortest one. And then finally, to close the loop, at some point, the application has to be able to tell Homa, I'm done with this buffer. You can reuse that space for additional messages. So that's the basic idea. And there were 4 challenges in this. First one is, well, how do we organize that buffer region? Second one is exactly how do we reclaim buffer space once the application is finished with the message that it's received? And then a couple of details. We want this to be pretty efficient, both in terms of buffer allocation. If you're allocating small message buffers at 100 gigabits per second, that's a lot of buffers per second that need to get allocated. So this needs to be super high throughput. And then we'd also like to make pretty good use of cache and memory space. So first, a couple of alternatives just to cover the space of design. So one obvious choice is, well, just allocate an array of buffers, each one of which is large enough to hold the largest possible message. In Homa, the largest allowable message is a megabyte, so you'd have to allocate 1 megabyte of buffers for that. That's really simple, but it doesn't use memory efficiently at all. And the problem is that, well, if you get a large incoming message, it'll mostly fill the buffer, but if you get a tiny message, it'll only use a tiny part of that 1 megabyte buffer. And that's really bad. For example, if you get a large burst of small messages, suppose you suddenly got 1,000 small messages that arrived. In order to handle that, you need to have 1,000 buffers or a gigabyte of buffer space, even though the actual space you need for the messages is really, really small. So that was not desirable. At the other extreme, we could do packet buffers. You just the buffer area is simply an array of packet buffers. And then when messages arrive, the transport spreads them out among various packet buffers. It takes several buffers here for the green message, and the brown message is small, so it fits in one buffer. We could do that, but the problem with that is packet buffers aren't very large. And so that means you end up, for large messages, passing a very large number of buffers back to the application. And so the metadata overhead, just to pass all this junk to the application and for the application to iterate over all that, that seemed like that would be problematic, particularly at high network speeds. You don't want to you want to be able to process things in really large chunks when you're processing big messages. So what Homa does is something in between that. Instead, the buffer region is divided up into, I call pages, but in order to avoid confusion with hardware pages, I call them buffer pages or B pages. And these are moderately big. Right now, they're 64 kbytes. So then, a couple of rules. A message, when it arrives, if it's smaller than one page, it will guarantee it will always be contiguous in a single B page. We'll never split messages across multiple B pages unless they are actually bigger than 64 kbytes. A large message will have to get split across a few B pages, but with the rule that all of those B pages will be full-sized B pages except the last page. Only the last chunk will be partial. So again, it's guaranteed to have full-size chunks, except for the last bit. And then finally, small messages can get packed into B pages. So potentially several small messages can get packed into a single B page. And so the idea of this is that first, it's memory efficient. If we're getting a lot of small messages, we're not going to use very many B pages. Second, it doesn't eliminate metadata. Large messages could still require several chunks, but there's not very many of them. At most 16 chunks for a full-size message. And then finally, which may be useful for applications, is that for any sort of meaningful application, you can be pretty sure the application level headers will always be contiguous, unless the message header exceeds 64 kbytes, which I suppose is possible, but I've never heard of that. You can be guaranteed that. So then in your application, you don't have to worry about, what if I have data structures in my header and they happen to cross a page boundary, and all that issue goes away. So then how do we reclaim buffers? Well, the answer is, first of all, when you call receive message, it will return you one or more pointers to these message fragments in the B pages. And Homa keeps a reference count for each of those B pages, which is the number of pointers with memory and cache efficiencies. So first thing is that buffer regions are pretty large. I'm not sure what the right size for these is. Right now, allocating 64 megabytes of buffer region. You need enough to handle whatever you think is the worst case scenario in terms of how many partially received or not fully processed messages you might have received. But Homa won't necessarily use all of that space. It tries to optimize. So when it's allocating B pages, it tries to use the ones at the beginning of the region in preference to the ones at the end. It'll only use the ones at the end of the region if all the others are in use. And so that means in cases where your application isn't actually using 64 megabytes of memory, in fact, those later pages they'll never even need to get mapped. They'll never be backed by memory. It's just virtual address space that's sitting idle. And in a really simple case, if you're just receiving small messages, you could get by with 2 or even 1 B page could be sufficient, so it won't use much memory. And this also should have better cache behavior as well, because we try and concentrate the accesses in a very small amount of memory in order to get better cache locality. So then the next question is, what happens since this buffer region is fixed in size? What do you do when it fills up? Well, the first thing we need to make sure we don't deadlock. So the worst case scenario is if we start allocating B pages incrementally as messages gradually arrive, you could end up with a whole bunch of messages that have allocated a few B pages, but not everything that they need, and we're out of memory and nobody can complete, and then we have deadlock. So instead, Homa allocates all of the space for a message when the first packet arrives. It reserves that to make sure we can't deadlock over the buffer space. But then what happens if there's not enough space? Then in this case, what happens is the Homa will queue that message. We'll put it on a queue. It will not allocate any B pages for it, and it will discard all the data packets for that message. So then when B pages become available eventually to handle the message and we can allocate space for it, well, first because of Homa's SRPT, we'll allocate space for the shortest message first. And then once we get the packets, or the buffer space for a message, then we'll ask the sender to retransmit packets. So when there's overflows, we'll end up with packet drops and packet retransmissions, which is extra overhead. But the assumption is this is a pretty unusual event. Shouldn't happen often, if at all. So performance-wise, there's not a lot to say here except that this closed the gap. Originally Homa was 10 to 11 gigabits per second, TCP 18 to 19. With this mechanism, Homa is now 17 to 19 gigabytes. It has a little bit more variation in performance than TCP does, and this is because, at least in the case of a single very long message, Homa's performance will depend a lot on which cores are allocated in the system for which parts of the message processing, and that can cause a little bit of fluctuation in performance. But it's basically the same performance as TCP. So a couple of issues that I haven't resolved yet. One is, how much memory do we need to allow in these buffer regions? As I said, currently I'm allocating 64 megabytes, but I don't know yet if that's the right number. And the second one is, what's the right size for B pages? I chose a size large enough that I thought that would be relatively efficient at 100 gigabit networks. But as networks get faster, you may want those regions to get larger so that you can have fewer larger chunks to deal with. The design is pretty insensitive to that size, so it's really easy to change that without really affecting anything very interesting. So just to summarize, this is just an example of exploring what are the system implications of using a message-based protocol rather than a streaming protocol. And as I said, the fact that Linux has structured itself around TCP streams, totally understandable, because TCP is the sort of the law of the land. But that's created a few conflicts for Homa, and this buffer management was one example of that. But fortunately, it was relatively easy to resolve. I was able to do it while remaining in the received message API, for example. I did not need a new kernel calls to handle this. I could handle it entirely with the existing received message. So that's what I've done. Happy to take any questions. Thank you.
I guess I'll start with the question. Okay, go.
I'm wondering, how does data get into the B pages from the NIC buffers?
How does it get into the B pages from the NIC buffers? Well, it still goes through SK buffs. So the SK buffs arrive into the Homa driver, and the Homa driver copies them out to the.
Okay, so there is a
There's still a copy there, unfortunately.
Can you look at the work for TCP receive zero copy?
I have not looked at that yet, but I'm wondering if this would actually might fit naturally with that.
It would be wonderful if you could eliminate copies altogether.
Yep.
The other thing is for the page size, kind of in the rest of the world, either like 4K pages, because that's the standard page size, or huge pages would be 2 megabytes. If you do go with some of these zero copy schemes, probably 4K would be the appropriate size, because then each packet would like have 1 or 2 of those pages, and then you can apply all the header data split and all the rest of that from zero copy. So it might be worth looking at that work.
Yeah, thank you. Good suggestion.
So I had a sort of question on the other side. So you said that you are going to use the buffer is now returned as a result, right? So clearly it's not receive buff or receive message buff, right? You're flipping the pointer that's coming back. So I'm going to ask a very controversial question in that case, which is we've spent a lot of time looking at whether TCP and sockets is the right interface. It sounds like a verbs type interface is the much more amenable answer, where you get to decide through a submission queue what your buffer allocation scheme is, and then return it as you need it, right? And if you're going to change the way buffs are being distributed anyway back, then what's the benefit of keeping the sockets interface intact?
You're saying switch to more like a receive queue and completion queue?
Yeah.
To me, that's only a matter.
Yeah.
Would be
it just seems like it's
indifferent. That's only a matter of what's most efficient. So
it will be more efficient
I would say
from that perspective.
we should
right?
pick whichever one is most efficient.
Yeah. Okay. Makes sense.
So with a lot of the buffer management slides, I'm getting deja vu from looking at IOU ring buffer management and registering buffers there. Can you contrast that? Have you looked at how similar the problems are in those spaces?
I haven't looked a lot at IOU ring, but as I was listening to the talk this morning, it occurred to me there were a lot of similarities there.
It really feels like it's almost the same thing, even to some point.
To add to the interface question on this side, I think it has similarities to the SO dev mem, which has a way to. It's also sort of an extension to the already complicated socket interface, and it has a way to post after the process is done with it these buffers back. But what I actually wanted to follow on was on Tom's comment about TCP zero copy receive. It made a choice to optimize for the large buffer copy to user cost by replacing with the page flipping, but small packets can still just be received in the receive message. Would that simplify your scheme so that you can basically have large buffers for large RPCs and the receive message that's outstanding and with a normal buffer posted is used for these small RPCs that come in and have to jump the queue?
That seems plausible. It seems like that would make sense, and that it seems like you don't want to use page flipping for small messages because the cost of the page flips is way higher than the cost of the copy. So, but I'm not familiar enough with how the zero copy stuff works to know how this would fit in that world. So that's a takeaway for me to look into.
Okay. Thanks.
What you said makes a lot of sense to me.
So Willem, that's page flipping we're doing for the large ones? Okay, so page flipping, basically we're modifying the virtual addresses. So the receive message would actually still have a buffer to receive in, but then when you do the receive, the addresses are just kind of flipped, so your virtual address is actually a kernel mapped buffer. It's kind of clever.
I'm curious if you know offhand, what is the cost of a page flip? And the ideal units is, what is the cost of a page flip in terms of bytes copied? You know, if I'm going to copy n bytes, how big does n have to be before the page flip is cheaper?
I think at one point Linus really hated this technique.
Mike. There was an analysis.
There was analysis done by Intel long back, 2005, I would think, where basically they implemented page flipping and it was slower. And the reason it was slower was you had to invalidate the TLBs of all the other CPUs.
Yeah. So, but the problem, I think, Stephen, you can't answer that question today. You can't actually take that data going forward because it's a function of MMUs and locks. And once you get into many CCDs and many tiles and many sockets, the cost can become absorbently high, right? Because you don't know what that implication of that flip.
I just wanted to point out the auth of that code is right there. I remember that. There was a Linux symposium, right? Yeah. And what's your opinion now?
Sometime later, we'll let John speak too. But.
Thanks, John, for the presentation. It's very interesting, and I'm interested to see if we can pull more of this together. Just mentioning that, yeah, I did a paper back in 2005 for PageFlip, but Dumaze put it into the kernel, right? So it's already part of the Linux kernel. This page flipping logic, it's well established. The thing is that it works really well for big MTUs that happen to fit the data portion exactly to a page, right? It doesn't work so great when you have to do like flip, 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 copy, flip, 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 copy, right? And the crossover point that you asked about, I think it was always like 2 pages.
2 pages, you said?
Yeah. So the mem copy, and of course, mem copies always get faster. So that data is pretty old now. So anyways, yeah, that's what it used to be. And it's going to be probably in that range, I would guess, still.
Yeah, we had some experience with zero copy on a research project called RamCloud that my group worked on about 10 years ago, where we actually implemented zero copy with RDMA. And it was really, really difficult to actually get performance benefits from it. Just really hard because the zero copy introduced additional overheads. It's particularly bad on the transmit side, where you have to have a way of somehow notifying back into the application that the information has actually been transmitted so the application can reuse the buffers. And we eventually kind of threw up our hands and we're not convinced that we could actually make it go faster. Now, it sounds like, though, zero copy has definitely come back to life in a bunch of settings, and maybe it is actually achieving performance benefits inside Linux. So
I can comment a little bit on the transmit path. So transmit TCP zero copy with message zero copy we use, and there we don't do page flipping, but page pinning. And essentially the magic constant is like 16K. Anything that's bigger than that, it makes sense to go into get user pages fast, because it's both the page pinning cost and the notification, this asynchronous notification that you don't need if you do a copy from user space into the kernel. So it's not the same case as page pinning, but yeah, it's also a couple of pages easily.
That kind of, though, that's TCP sockets again, right? Like same. If it is a user space supplied buffer, you don't have that problem. You can pre-pin and carve earlier, right? So I think the zero copy transmit can be made effectively totally free. The question with receive is page granularity, and that's why I was saying. So now if you go down the RDMA interface, you don't have any of these problems, because the general theory is you supply a pre-pin, pre-packaged buffer area, and the application carves it and delivers it, and then it's just a ring that's sharing the pointer back and forth. You're not going to do any MMU flips. You don't have to do page flips. It's already in your MMU always.
Somebody? Okay, I'll ask a quick question, John. There's some people asking, when are you going to upstream code?
Sorry?
I'm just speaking on behalf of a friend.
I have a friend who wants to. When it's going to be upstreamed?
Yes.
It's on my list.
Hello, thank you for the talk. I was a bit more curious about the when you mentioned that there are multiple small messages that can fit into a B page, right? So you would also have some metadata overhead of identifying like multiple different messages that are stored. How do you think that impact would play out, considering you still have that overhead?
It's pretty straightforward in that having multiple small messages in a B page means 2 things. First, it means the reference count can be higher than 1 for the B page. And then we just pass back pointers to the application for those individual messages. And once we've passed back the pointer to the application, we don't really even care about what those pointers are. All we care about is that the application eventually tells us so we can decrement that reference count by 1 when it's finished with it.
Yes, but would that also not result, let's say, this is assuming that the application is programmed incorrectly, then you might also end up reading another half of the message which was not yet completed, right?
I see. What if the application is misbehaved? So there's no protection between these messages, but they're all going to the same application. And so that's no different than, the current scheme where we copy things back in the application supplied buffer. The application might read beyond the end of that buffer, and it's just hurting itself. So I don't think that it creates any particular problems. A misbehaved application will still be misbehaved. I see it as a message on the network from, will this design make the Homa API too complex for an average programmer to use? I would say average programmers shouldn't have to see this. In fact, there's actually a C++ library package that comes with Homa now that handles all of the buffer management for you automatically. You just call it to receive messages, and basically you get an object back that represents that message, and when you delete the object, the package will automatically take care of returning the pointer back to Homa. So this is the kind of thing I think that can easily be covered with a very nice, simple application API.
Was it taken off now? The question that it's been answered? Okay, I'm sorry.
Okay.
Questions? Otherwise, let's thank John.
Thanks.
Thank you.